3, 2, 1, let's go. Alright. Chapter 5, Linear Algebra. Let's do it. Okay, so, as you can see, we will introduce linear transforms. So, this is, without a doubt, the single most crucially important chapter out of our textbook. This material is truly what linear algebra is all about. Even though we've been using matrices for a lot of things, we're going to basically now see that matrices were actually just a very specific example of something. And you can probably guess what they're an example of. So before we formally define what a linear transform is, let's see some examples. Alright, so for the first one, let's think about a function from R2 to R2 that does the following. You give me an element of R2, that's an ordered pair. Alright, it's got two components, an x1 and x2, and I can create a function by hitting that second coordinate with a minus sign. Alright, and note that if you want to think about geometrically what this function does, it reflects things across the x-axis, right? So the point 1, 2, we think about that living in the first quadrant. The output of the function is 1, negative 2, which lives in the fourth quadrant, so it reflected it across the x-axis. Similarly, the point negative 3, negative 4 lives in the third quadrant, and then when I feed it into f, it reflects it up across the x-axis, now living in the second quadrant. Okay, so alright, this is an example of a linear mapping. Specifically note that if I fed it a scaled input, so note that if you scale an element of R2, you scale coordinate-wise, you get the following. Got some parenthesis missing there for do it live. And, there we go. Now it's beautiful. Alright, yeah. So, yeah, you scale the coordinates themselves, and hey, this scalar can get pulled out of the whole thing, and then, oh, look at that, it's just f of x. So, scaling an input is the same thing as scaling the output. Okay. So, in other words, the function f respects scaling. Another word that's used for this sometimes is f is homogeneous. And if you've taken differential equations, you know that that word just kind of gets thrown around all over the place, with good reason. Perhaps it's all related to this fun stuff. But anyway, so another property that this particular function has is that if I feed it a summation, right, things that we can do in Rn, we can scale stuff, we can add them. If I feed it a summation, right, remember the summation of two things in Rn is coordinate-wise summation. And we can pull this apart accordingly. Specifically, we see that the output at a summation is the summation of the outputs. So in other words, f respects addition. Functions that do that are usually called additive functions. That's pretty standard. Calling this homogeneous is not too much. Some people say respect scaling, or you can pull scalars out. But this being additive, that's pretty standard nomenclature. Missing a period, but I'm not gonna care about that. But anyway, all right, here we have a nice function. It has a nice geometry to it. It's a reflection, and here we see it respects scaling and it respects addition. All right, let's look at another example. Oh, matrices. Hey, my favorite matrix: 1, 2, 3, 4. Well, we can create a function from R2 to R2 by simply taking an element of R2 and multiplying it by the matrix A. It's a little harder to get an idea of what this looks like. Right, it's a function from R2 to R2, so its graph lives in R4, so you can't really envision it. So what you could do is plug in some stuff from R2 and see where it ends up if you want to get an idea of what this function might do, but I don't know. But anyway, we do know that it will do a couple of things. So we just talked about respecting scaling and respecting addition. So if you feed in a scaled vector, remember scalars and matrix multiplication, we can just move the scalars wherever we want. You can pull them inside and outside of matrix multiplication, and oh look, the output of a scaled input is the scaled output. Right, and obviously the same thing flies for addition, right? Matrix multiplication is distributive, so the fact that f is additive is not surprising. Okay. Another one. All right, let's let D, 0, 1 be all of the differentiable functions defined on the set 0, 1, and then we'll let R, 0, 1 there be just the set of all functions. Now, obviously, what I'm going to define here, I'm going to let T be the function that maps our function to its derivative. So note this is a function that takes functions as input and outputs functions. Okay, right, and hopefully this immediately conjures up Calc 1, because hopefully your Calc 1 professor noted that differentiation is a linear process, meaning that the scaled derivative is the same thing as the derivative scaled, and the sum of derivatives is the derivative of the sum. So this mapping T, again, respects addition and is additive. That's the same thing. Respects scaling and is additive. Yeah. So it's, again, a mapping that's respecting the two key ingredients of what a vector space is, right? You've got scaling and you've got adding. And this mapping treats it right. Takes it out to a nice seafood dinner. All right, well, one more. Differentiation is linear. So is integration. So specifically here, note the difference now. This transform that I've created, every continuous function can be integrated. Note that I'm taking functions and creating a real number here. So I take functions as input and spit out real numbers. Right, and if I scale the function, I can pull the scalar out of an integral, and if I add two functions up, I can pull out I can break up the addition, the integration over the addition. So here we see this operation respects scaling, respects addition. So again, it is a nice mapping. Okay, so now we have seen four examples, four very different examples. So here a mapping from R2 to R2 itself, directly messing with the input. This mapping, which was created using matrix multiplication, this mapping, which we created using calculus, and this one as well. Now, this one, to note, the output is a real number, whereas for this one, we were outputting a function. So, interesting. All right, well, we've seen four different functions in wildly different settings, and these functions all shared a commonality. They respected scaling and they respected addition, the key ingredients of a vector space. So, probably a good idea to give something that does that a name. So, given vector spaces V and W, a function between them is linear if it respects scaling, so you can pull scalars out, and it's additive, it respects the addition. Okay, so there it is. Stare at that and digest it. This might seem like nothing to you, but at first, right, because at first glance, this is just, well, yeah, that seems like a reasonable thing to look at. I can't even begin to stress how fundamental this is to mathematics, period. Right, not just to linear algebra, and hopefully you're starting to realize that linear algebra is very pervasive in mathematics. Almost all of math hinges on linear algebra, one way or the other. I can't even begin to tell you that these are, it's like, there's so much math that you can go, this is very important. This is, beyond important. This is beyond essential. This is, beyond elemental. This is, this is, not even, the atoms. These are, the subatomic, quark nonsense and your, hadrons and, all that other goofball stuff. Right? So, the goal for this chapter is to thoroughly and utterly study these things. All right, so linear mappings, they're also called linear transforms. They are essential, incredibly. All right, and hopefully as we go, you're going to be very convinced of that. So before we go forward, some nomenclature that is thrown around. A linear function whose domain and codomain are the same is usually referred to as a linear operator. So if you hear anybody talk about operator theory, that's what they're doing. They're playing around with linear functions from a vector space to itself. And speaking of something that somebody may have mentioned, we already just saw an example of this. When the codomain is the real numbers themselves, that's what a functional is. So, I've talked about functional analysis before. This is what you study. The key ingredient there are these things right there. An entire branch of mathematics devoted to just this. And it's a good time. So, like I said, we'll have a bonus content week. And I'll let you in on the little secrets going on here with functionals, but we'll keep a pin in it. So speaking of functionals, the new problem list that's been posted, I put my favorite problem about functionals as an optional problem. I was going to make it a required one, but then I thought about it a little more. I'm like, no, I think that one might be too hard. It's not hard, but it's one of those, like, yeah, you'll see. And when you play around with it, you'll be like, oh yeah, thank God this wasn't a real homework problem. Anyway, okay, so let's start goofing off linear functions. Okay, so the first thing that I want to do is quickly point out two facts about linear functions that we're kind of just going to throw around and just, they're there, we're going to use them. So the first one is that it sends the identity element to the identity element. And the other one is, we know it respects scaling, so it's worth stressing that it respects subtraction. All right, the proofs here are quite easy. And I'm going to note that there are other proofs that you can do for these. These are the proofs that I wrote. So to see that t of 0v is 0w, well, just remember that 0v plus 0v is itself, and t is linear, so it respects addition. So that splits up accordingly, and subtract one, and then do the cancellation, you get 0w. You also can pull this off by noting that you can pull out the scaling. So 0v, remember, is equal to 0v times the 0 real number, and then you can pull the 0 real number out. That's another way of doing it. Speaking of friends from grad school, I never think of it that way. I always think of it in this additive way. But that scaling trick, my buddy Jake, he showed me that once. I was like, oh, that's lame, but it also works. And then you can do the same thing for subtraction, because remember, negating v is the same thing as scaling by -1, and you can pull out the scaling, but you can also get it from the additivity itself. And again, that's how I always think of it. So here you see the proof. The 0 vector in w by a, we know is the 0 vector in v, but we know that's v minus v, and this respects addition, right? Subtraction, again, isn't a real thing. You're just adding by the negative, and then subtract that over the other side, and there you go. All right, so like I said, both of these can be alternatively proven using the scaling, but I use the addition property here. All right, cool. All right, and note something here. This tells me something else about linear functions. Remember, a function is called odd if it pulls out negatives. So this actually tells you every linear function is odd, which has peculiar consequences in certain situations. Speaking of unsolved problems, I've got a weird one, and we'll talk about that in the bonus content. Okay. There's another characterization for linearity that is a little bit more streamlined, where rather than verifying both the scaling and the addition separately, just do them both at once, and that's this following criterion. So a function is linear if basically it respects linear combinations. So if I feed in a linear combo, its output is the linear combo you think it should be. Okay, so it's an if and only if, so we got two things to do. So let's start off. Suppose f is linear. All right, well, then, yeah, it works, right? It breaks, linearity means we respect addition, and then we respect the scaling. And that's it. Super forward direction, super easy. Now, the reverse direction, suppose that our function does respect linear combinations. We want to verify that it's linear then. All right, well, as you can see, you can show scaling works by putting a 0 in the appropriate spot, and likewise addition will work by placing 1s in the appropriate spots. So there you go. Not the most enthralling proof, right? This is just a literal unravel the definitions, and not even like an exciting unravel the definitions, right? Because we've seen some unravel the definitions where it's kind of like, ooh, this is a different way of thinking about it that leads to these equivalencies that are nice. This is one of those results where it's just going to be nice it's just going to be nice to have this characterization for linearity. So when we want to prove something is linear, we don't have to spend that much time dealing with it. Rather than doing two separate things, just get it all taken care of at once. Okay. All right. Now, speaking of linear things, linear functions, respect scaling and respect addition, we have previously discussed a mathematical object in vector spaces that respects the scaling and respects the addition, and I already spoiled it. Those are the subspaces. So I want to quickly revisit subspace and explicitly prove two things that I've sort of implicitly stated in class, but I never actually outright proved them. So let me just do it. So the first thing I want to prove is kind of this analogous result to what we just proved. So a function was linear for respects linear combos. Same theorem can be proven for subspaces. A subspace is precisely the subsets that respect linear combos, and I want to stress the non-empty assumption. We are going to use this. Okay, and again, an if and only if, so I got two things to do. All right, well, if you're a subspace, then given two things in the subspace, they can be scaled into them, and then they can be added up into them. So, right, a linear combo, the ingredients there are scaling and then adding. Right, and note that kind of what we're proving here with these two results is that linear combos, even though they're made out of scaling and adding, linear combos break down to adding and scaling. So it's a two-way street. If you've got a linear combo, you can break it down to its ingredients, and vice versa. You can start with the ingredients and build your way up to a linear combo. All right. Cool. So that's the forward direction. What's the reverse direction? So suppose that we can actually do what we're supposed to do. And again, another freaking typo. Gotta be real careful. If this was in class, I would have outright said the F word right there. But these are getting posted. I know. I don't want my colleagues to know that I swear all the time in class. Don't tell nobody. All right, so suppose that our subspace is closed under linear combinations. All right, then when we scale x, we can glue it together accordingly, and when we add, we can break it up accordingly. So note it's exactly what we did for linear functions. Okay. And we want to now stress that we are a subspace, and we're done because of the non-empty assumption. All right. So remember, a subspace needs to be a non-empty set satisfying these two things. So if I did not start off with non-empty in my hypothesis, I'm not actually done, because the empty set vacuously satisfies this condition, because there's nothing in M, so you can never actually do this, so it's just vacuously true. So we're actually now, at this point, implicitly using the fact that we assume non-empty to guarantee that we're a subspace. So, all right, nice. So speaking of the non-emptiness, something that we've used but not explicitly proved, and this is supposed to say M is a subspace. Jeez. Man, I go for these slides. I go for these slides like a lot, and it's just this. My wife busts on me for taking so long to make this, because she takes 4 seconds to make slides, and she much better at teaching than I am, I guess. Anyway, yeah. So something that we've explicitly used, and here we're again explicitly using the non-emptiness. We can fix an x in there, and then you can scale it by 0. That guarantees a 0 vector is in there. So we've used this fact a couple of times, but we haven't outright proven it, so here you go. And we actually need this for the next couple of things we're going to prove. Okay. Alright, so what's up next? So up next, is a couple of facts about linear transforms as functions. So recall that if I have a function, the image of a set is just the outputs whose inputs have been restricted to that set. And specifically, the range is the image of the domain. So remember, when you set up a function, the y here is not necessarily the range. The y here is its codomain. This is anything that contains its range, right? So f of x is definitely contained in y, but y could be significantly larger, right? So if you think about like x squared, its codomain is the reals, but its range is the positive reals. So. Anyway, so it turns out that not only do linear operations respect linear combos, they respect subspaces in the following sense. The image of a subspace under a linear mapping remains a subspace. All right. So how does this go down? Well, I want to prove something as a subspace, and what I'm going to use is that new characterization of subspaces that we just talked about, because it works quite well with f being linear. Okay, so the first thing to note is, oh hey, by the way, since you're a subspace, we know we've got the zero element in there, and as we just verified, a linear mapping respects the zero element, sends the zero element to the zero element, so we know that f of m is non-empty, it's got the zero element in it. That's nice. And now we need to verify that it is closed under linear combos, so pick scalars alpha and beta, pick elements z and w out of f of m. Okay, if you're in the image, that means there are inputs so that you are outputs for your function. And then we use the linearity because we know that the linear combo has to be in M, because M's a subspace. The function's linearity then guarantees that the linear combo of Z and W lives in the image of the subspace. And bing, bang, boom, proof is done. We verified the set's not empty. And then we verified that linear combos do not escape the set. Therefore, it's a subspace. Nice. Okay, and now this style of proof, I really want to stress something about this particular style of proof. There are so many proofs about linearity that basically go exactly like this. Because not only do you study linear functions as just like functions, there's also looking at the images of linear mappings. And like I said, in the bonus content week, we're going to talk about some fun unsolved problems. We're going to talk about the granddaddy of unsolved problems in linear algebra, and it has to do with images of subspaces. It's astounding when we talk about it why it's still unsolved, but we'll get to it. Okay, so speaking of images, we can go backwards. Remember, the inverse image, or the pre-image, or the pullback, this has a bunch of names, is the set of inputs whose outputs land in the set B. Right, so note the difference. Right, the image is a subset of the codomain. These are the outputs. The inverse image of a set is the inputs whose outputs land in the set. All right, and to no surprise, we're basically going to prove the exact same theorem, but there's some key differences to note. Now the subspace lives in the codomain. All right, the inverse image of this, I claim, is a subspace. Okay, so we prove the image of a subspace remains a subspace under a linear mapping. The same is true for the inverse image, or the pre-image, however you want to call it. Right, again, note this is a subset of the domain. Alright, so let's prove this. And again, the first thing I want to verify is that, by the way, there's stuff in this set, right? In order to be a subset, we must be non-empty. And again, we're going to use the fact that the linear functions send the identity to the identity. And that is a big old typo right there. Let me fix that. Right, we send the zero element of E to the zero element in W. That has to live in the subspace M. So that means, oh yeah, that's even more of a typo. I should have fixed that while I was right there. Oh boy, oh boy, oh boy. Yeah. There we go. Ooh, did I screw up the previous one? Let me see. I did that one right. So, there you go. I'm not even consistently wrong, jeez. The best kind. Alright, we've got now that the inverse image of a subspace has 0 in it, so we know it's not empty. Now we just need to verify that it respects linear combos. So again, we'll set it up, pick 2 things out of the reals, pick 2 things out of our set we're suspecting is a subspace. All right. Now, because we live in the inverse image, that means the outputs have to live in M. And now by the linearity, because the outputs live in M, that means the linear combo lives in M. That ensures that linear combos do not escape the inverse image, right? Because their output lands you in the set M. Nice. Okay. So again, note that this proof is like basically identical to the previous one. The only thing, the only real difference here is minding your P's and your Q's, right? Paying attention to where things live and where they're coming from, and right, note that I caught myself goofing up there, right? That the inputs, right, the pre-image lives in the domain, so that should have been the 0 element with respect to V, not the one with respect to W. All right. Okay, 2 more slides to go. A little short video today for you. Okay, so there is a inverse image that is of incredible importance. Your textbook waits till later in the chapter to introduce this, but that's because this book is oh, I don't care if this one's on record. This book sucks. This book is garbage. I'm gonna email the people who wrote it maybe and be like, your book is bad and you should feel bad. I'm not actually gonna do that, but if they ever watch this video, that's my opinion on your textbook. Anyway, they wait too long to talk about it, but an inverse image that's incredibly important for a linear mapping is what's called the kernel. And these are the things in V that have to get mapped to the identity element over in W. Now, we've already talked about for a linear mapping, we know there's stuff in the set, but we can actually do one better. This has to be linear. This has to be a subspace. And in fact, this is the subspace. This is the single most important subspace in vector space history. Right, we're going to prove a humongous theorem about this a little bit later on. And if you squint at this a little hard enough, this may look super familiar. May have something to do with solving a certain matrix equation, where the right-hand side's equal to 0. Just maybe. Anyway, so the fact this is a subspace, we actually don't need to do any work. We've already proven that. Note that it's the pre-image of the singleton that only has the identity element for W. Right? If you're in this set, then you get mapped to that singleton, which means you have to equal what's in there, and vice versa. If you're in the kernel, you map to the set. So it's the pre-image of that. And, hey, as we've discussed, that is a subspace. It is the trivial one. It's the boring subspace. So, hey, pre-image of a subspace has to be a subspace. Kernel's got to be a subspace. Boom. It's our feeling that you can directly prove this if you're so inclined. But, yeah. Right, yeah, we prove theorems to use them, so let's use it. There's side note on this. So there was a professor at Kent State University named Joe Dietzel. He is no longer with us. I saw him give a talk, and it was the funniest math talk I've ever been to. He was talking about Banach limits, which are some ridiculous things, and just his attitude, and like just like me, I guess he just would randomly go off on tangents. Like he didn't even get halfway through his talk. He only got halfway through the slides. And he's like, if you care about this, you talk to me later. Because he was just like talking about all this other random stuff instead of what was on the slides. No idea who that reminds me of, but anyway, he has a book about absolutely summable series, and he begins the book. I don't know if it's somewhere in the book. There's like some theorem that he invokes that's like really ridiculous, and he basically says something to the effect of the gods wouldn't let us prove theorems unless they wanted us to use them. So that's a fun little thing for you. All right, so let's wrap things up with an essential property of linear mappings. Everything I've just talked about is serious stuff when it comes to linear mappings. It may not seem like it right now. It might just be a lot of I'm just unraveling definitions, but I'm planting seeds. I'm starting fires everywhere. You know, we're gonna get some good stuff out of all of this. All right, so the last thing I want to verify, and this is some more function-heavy stuff, is that the composition of linear functions remains linear. So, in some sense, there is this huge parallel between linearity and continuity. Right? Remember, the composition of continuous functions remains continuous, right? And in fact, for the category theory fans, they're all kind of talking about the exact same type of object, but I don't want to go any further in that nonsense. Alright, so this is just straight up unraveling the definitions. I want to verify the mapping's linear, so show that it respects linear combos. And hey, there you go. Read it. There you go. This is not a particularly enlightening proof. This is literally just, well, you feed in a linear combo. The composition of two functions is, well, you feed me in an input, and then I get an output, and then I put that output inside of this other function as its input. F is linear, so it pulls it apart the way you want it to. G is linear, so it pulls it apart the way you want it to. And, oh, hey, look, the composition then has to pull it apart the way you want it to. So, it's not the most enlightening or exciting proof, but it's a very important one, and it's something we want to actually take the time to prove. Alright, so there we go. Our introduction to linear mappings, prove some basic properties. And, yeah, that's all about it for today. So, I'll see you next time, where we're going to discover that linear mappings and matrices, I bet they're the same thing. Alright, I'll see you next time.